Hi there, this is exercise 19C. I'm splitting it into two parts. This says differentiation and integration with 2D vector problems. But I think from memory we do one with differentiation and another with integration. So I'm not sure how many questions there are here actually, but notice this little graphic. This graphic sums up what we're going to try to do. We have got an expression very often is given to us, like for the displacement, for instance. And that displacement, we need to know that if we ever want the velocity, we have to differentiate it. This is the basic idea. And this differentiation will get the velocity. But if I differentiate the velocity, then I'll get the acceleration. A is dv by dt. And these two equations are effectively the ones which I'm going to use to do this. Notice effectively if you write it in that order xva, if ever you want to go to the right, you're going to differentiate it, and by definition then presumably if we ever want to go to the left, we're going to integrate, because integration of course is the opposite of differentiation. So these two things, oh don't forget plus c by the way when you come to do your integration, but we're not doing integration today so it hardly matters about that. So here down on this bottom bit, it does actually say this. It says if you are given v, or if you want v rather, you differentiate the x. But notice the x may be a vector, and if x is written as some vector, maybe 4t and 2t cubed, then to get v I've got to differentiate both parts. So I differentiate the 4t, that's 4. I differentiate the 2t cubed, that would be 6t squared, and you can see it's relatively easy to do, and I just differentiate it and that will get me it. I've got a similar trick with the a can be differentiate the velocity, or think of it as differentiating the x value twice. So let's on that basis do a question. It says a year 12 example. Now this then was what we saw in year 12, because this method isn't unusual for us, it's not new. So it does say a particle moves in a straight line with velocity here. So there's my velocity equation. Find the acceleration. Well, if I want the acceleration, I'm going to find dv by dt. And of course now we've got more complicated functions. I suppose that's the thing I would say is the major difference between year 12 and year 13, is we've got more complicated functions and we're going to potentially use vectors as well. So differentiate e to the t, actually you get e to the t, it's not hard at all, that 2e to the t, it's a nice one, minus t squared. Now that does become something different, that's minus 2t. It says t equals 3, so therefore when t equals 3, a equals, well, 2e cubed minus 2 3s are 6. Now usually in A-level mechanics type questions, these type questions, you would work that out as a decimal. I think it doesn't say exact answer. If it said exact answer, 2e cubed minus 6 is right, but I'm going to use the e button, which is above the natural log button, the ln button. 2e cubed take away 6, 34.2 to 3 significant figures. Doesn't say what this is in, presumably this is meters per second squared, but doesn't tell me really. Find the expression for the displacement from the starting position. Now this is an interesting one then. This is going back to what we said before. In order to give us the displacement, which is really what it's after, notice it says v, so we have to get the x, and x is the integral of the v dt. Remember we saw, don't forget the plus c. So if I integrate 2e to the t, well I actually get 2e to the t again. It's a really nice function. But this one becomes t cubed over 3, and don't forget plus c. Now it does say from the starting position, and that's another way of saying really we can set the starting position to be the origin. So the way to write that is x is initially at 0 0, and therefore if you put 0 into this, I would get 0 0 is equal to, well, let's do it, that's 2e to the 0. That's the difference between what we've seen before and now. I don't know why I've switched to a vector, by the way. This isn't a vector. This is just 0. But either way, it's 0 equals 2e to the 0 minus 0 plus c. And I was just saying there that unlike where we've done it in the past, the kind of functions we got asked to integrate and differentiate, if you put 0 in, you've got 0 out. But now we've got more complicated functions. This proves that it's not always the case. 2e to the 0 is actually 2 plus c, and therefore c is minus 2. And therefore the expression which I'm going to write down here, because I don't want to run out of room, is x equals 2e to the t minus t cubed over 3 minus 2. That's what I think it is anyway. Oh, up here, 2e to the t minus a third, minus c. Oh, interestingly, I've worked out what the c was. But they didn't bother. I don't know if that's because I've been overly keen or not. I don't know. Anyway, here's some questions. A particle moves in 2 dimensions. A displacement from its starting position measured in meters varies. Now notice this, by the way. I was using x. X can be written as s, can be written as r. There's a variety of letters used for the displacement. This example uses r. So just look out for the fact that you kind of need to know that it can be written in any of these. R equals this. And it wants the speed. Now, the speed is linked to the velocity, so I think I need the velocity, and that then is the differentiated version of what I've got, which is dr by dt. Differentiate the top. I get 4t. The 4 disappears. Differentiate the bottom. The 1 disappears. Minus 3t squared. And that's it. That's the velocity. So is that it? Well, no. For 2 reasons. First of all, they tell me t is 3. So I can work out the velocity at this point. It's 4 3s are 12. And 3, if I substitute that in, that's 9. I think minus 27. So is that it? Well, no, still no, because this is the velocity. I want the speed, and this comes down to Pythagoras again. And I keep on drawing these little pictures. It goes 12 across, and it goes, the velocity is going 27 down. So my speed will be the square root of 12 squared plus 27 squared. No idea what that is, so I'm going to do it now. 12 squared plus 27 squared equals square root of the answer equals, and it says 29.5, give or take a bit, 29.5. And the speed is meters per second. 29.5 meters per second. Second question. When using integration with vectors, the constant of integration will be also a vector. I thought we was going to just do differentiation today, but this proves we're not. We're doing a mixture of the two. That's fair enough. So a particle moves with acceleration this. So its initial velocity is this. Alright then, so we've got 2 pieces of information. The important bit is that A equals something. And A equals this. So in order to get our velocity, which is what I actually want, I have to differentiate. I nearly went wrong there. I have to integrate the A with respect to t. So I'm going to integrate A with respect to t. So this is the backward version I was talking about. And if I'm going to differentiate A with respect to t, then I'm going to have to add on the power and divide by that too. So it's going to be 2t squared over 2. I reckon that is t squared plus 1. If I add a power onto that, I reckon I get plus t. With sine, cos, minus cos. If I integrate sine, which I've got on here, I get minus cos. So this is minus 2 cos t. Okay, a lot of people here would think that's it. Actually, it's not. We've got to do a vector. I'm going to write C1, C2. We're going to find these 2 numbers. And the way we do it is we are told the initial velocity. Notice initial velocity is when t equals 0. Therefore, v equals, I can write t squared, which is 0, plus 0. So that's 0. That was easy. And minus 2 cos t. Well, cos of t, again, this is another function where if you put 0 in, you don't get 0 out. This is minus 2 because cos of 0 is 1. Plus my C1, C2 has got to equal, what did it say? Oh, it equals that. It equals minus 1, 3. So just do the top line. I've got C1, I reckon, is -1. And the bottom line, C2, is, well, if I move that over as a plus, I reckon 5. So my final function then, I reckon, is v equals t squared plus t minus 1. I can join them together at this point. And for this one, I'm going to write minus 2 cos t plus the 5. I could probably put 5 minus 2 cos t if I preferred. Find an expression for the velocity. I think I've done it. And that's exactly what I've got. I always like it when it's exactly right. A particle starts from point P with velocity 3,1. So v equals 3,1 initially. Its acceleration is given by that. Determine whether the particle ever returns to P. Well, first of all, I need to get the velocity. So velocity equals I did it again. It's the integral of a dt. So that's the integral of minus t to t dt, which equals minus t squared over 2, and 2t squared over 2 would be t squared. So, but then don't forget your constant, and your constant is a two-dimensional constant, c1, c2. We are told its initial velocity is 3,1. So just using this, when that equals, alright, and so t equals 0, its initial bit, that's what that stands for. V is 0, and I like those because both of them are 0, we put 0 in, plus my c1, c2, and that equals this initial velocity is 3,1. So if that's true, my velocity now, because you can see c1 is that, c2 is that, I think my velocity is now minus t squared over 2 plus the 3 and t squared plus the 1. That is my velocity vector. Determine whether the particle ever returns to P. Well, to determine that, I suppose I've got to know about x. So x is the integral of v dt. And I've therefore got to integrate this again. And to get that, I'm going to write minus t squared over 2 plus 3. This is all going to be integrated. And t squared plus 1 respect to t. So if I integrate it, I get add a power divided by the power. I get t to the 3 over 6 plus 3t. Hopefully you agree with that. I get t cubed over 3. I was wondering that that's a minus one, isn't it? I just realised that's a minus there, so that's a minus squeezed into there. Plus t. Plus a new constant. Alright, C3, C4, just so I don't get confused between all my constants. Do I know of anything? It starts from the point P, so it's at point P. When will it ever return to P? I think that means this constant can be ignored, because we're just going back to where we started from. Effectively, we're at the origin. So I can ignore this point. So if that's true, it's really saying when is this equal to 0? So I've got minus t cubed over 6 plus 3t is equal to 0. And also t cubed over 3 plus t has got to equal 0. So presumably, if we get the same answer to both questions, then the answer is yes. If it will go back to 0. But if not, then it won't go back to 0, because we've said this is equal to 0, 0 effectively. So let's see, let's answer this question. Well, I can take out t as a common factor. I get minus t squared over 6 plus 3 equals 0. So obviously t equals 0 is 1, but that's no good because that's when it starts. The other one is when I'm interested in. I've lost my pen somehow. Oh, I've nearly run out of time. Well, I'm going to leave it. I've just realised I've nearly run out of time, so I'm going to leave this to you. But it might be that we get a value for t, we get a value for t, and then we can determine if it's the same value of t, then it does go back. If it's not, it's not. So that's a nice place to finish that question. There's lots there, and we've got another example as well. I do like the fact we've got some examples, because particularly it just gives me something to talk about during the lesson. So anyway, exercise 19C.1. There is another one I think coming as well. Cheers for that.